A function of several variables is a rule that takes more than one input and produces exactly one output. For example, the height of a hill could depend on both how far east you walk and how far north you walk, so the height is a function of two variables. A partial derivative measures the rate of change of that output with respect to one input variable, while every other input variable is held completely fixed. In plain words, we ask, if I only let one variable move and freeze all the others, how fast does the output change? Picture the function as a curved surface floating in 3 dimensions, like a hill made of graph paper. Now watch as that same hill flattens down into a 2-dimensional contour map, where each curved line on the flat map represents a fixed height on the 3-dimensional hill. Let us work through a full example. In words, our function is the output equals x squared times y plus y cubed. In symbols, that is f of x, y equals x squared times y plus y cubed. Step 1. Find the partial derivative of f with respect to x. To do this, we treat y as a fixed constant number and differentiate only the x parts. The term x squared times y differentiates to 2x times y. The term y cubed contains no x at all, so it differentiates to 0, so the partial derivative of f with respect to x equals 2xy. Step 2. Find the partial derivative of f with respect to y on its own line, one step at a time. This time we treat x as a fixed constant number and differentiate only the y parts. The term x squared times y differentiates to x squared. The term y cubed differentiates to 3y squared, so the partial derivative of f with respect to y equals x squared plus 3y squared. Now for the check step, we substitute specific numbers to confirm these formulas actually make sense. Let us choose the point where x equals 2 and y equals -1. Substitute these values into the partial derivative with respect to x. 2 times x times y becomes 2 times 2 times -1, which equals -4. Substitute the same values into the partial derivative with respect to y. X squared plus 3y squared becomes 4 plus 3, which equals 7. Now let us confirm these numbers make sense against the original surface. First, find the actual value of the function at this point. X equals 2, y equals -1, f equals x squared times y plus y cubed, which is 4 times -1 plus -1, giving -4 minus 1, which equals -5. Next, nudge x slightly to 2.1, keeping y at -1, and find the new function value. F equals 2.1 squared times -1 plus -1, which is -4.41 minus 1, giving -5.41. The actual change in f is -5.41 minus -5, which equals -0.41. Compare this actual change to the prediction from our partial derivative. Our partial derivative with respect to x was -4, and the small step in x was 0.1, so the predicted change is -4 times 0.1, which equals -0.4. -0.41 is very close to -0.4, so the check confirms our partial derivative with respect to x is correct. So to summarize, the partial derivative of f with respect to x equals 2xy, and the partial derivative of f with respect to y equals x squared plus 3y squared. Both formulas were confirmed by substituting real numbers and checking the predicted change against the actual change on the surface.